Welcome again to the European Non-Associative Algebra Seminar. I'm happy to introduce the speaker of today, Professor David Towers from the Lancaster University. The title of his talk is Zinbiel Algebras are Nilpotent. Please, David.
Well, thank you for inviting me to give this talk today. Rather like last week's speaker, I'm recovering from a chest infection, so I apologize if I have to cough or clear my throat at any point. Well, I want to talk a little bit today about, now, why is that not moving? I want to talk a little bit about Zinbiel algebras. But first, I need to remind you about Leibniz algebras. So recall that an algebra L over a field F is called a Leibniz algebra if for every x, y, and z in L, we have x times yz is xy times z minus xz times y. So here I'm using this bracket notation to denote the product in the algebra. In other words, the right multiplication operator is a derivation of L. And as a result, such algebras are sometimes called right Leibniz algebras. And there's a corresponding notion, of course, of left Leibniz algebras, which satisfy the identity that x times yz is xy times z plus y times xz. Clearly, the opposite of a right Leibniz algebra is a left Leibniz algebra and vice versa. So in most situations, it doesn't matter which particular definition we use. And Leibniz algebras which satisfy both the right and the left identities are sometimes called symmetric Leibniz algebras. The Leibniz kernel is the set, the span of the set of squares of elements, x times x for x in L. And this is the smallest ideal of L, such that L factored by I is a Lie algebra. And it also satisfies that if you multiply on the left by any element of L, then you get 0. And then much of the theory of Lie algebras can be generalized to Leibniz algebras. Though, of course, the focus is not so much on those with a trivial radical R, as they're all Lie algebras, because the Leibniz kernel is an abelian ideal, and so that's sitting inside the radical. Well, an algebra Z over a field F is called a Zinbiel algebra if for every x, y, and z, we have that the x times y times z is the same as x times yz plus zy. I'm going to denote the product in a Zinbiel algebra by this circle notation. And strictly speaking, what we've introduced there is a left Zinbiel algebra, and there's a corresponding right version, of course. An algebra is a right Zinbiel algebra if for every x, y, and z, we have x circle yz is xy plus yx times z. And Zinbiel algebras were introduced by Loday in 1995, though he called them dual Leibniz algebras. And I'm going to restrict attention today to right Leibniz algebras and to left Zinbiel algebras, as that's what Loday did. Well, Ginsberg and Kapranoff introduced and analyzed a concept of Koszul duality for operads. And starting from this concept, it was proved by Loday that the dual of the category of Leibniz algebras is defined by the category determined by the Zinbiel identity. And that was essentially the content of the following result due to Loday. That if you take a right Leibniz algebra L and a left Zinbiel algebra Z, and you form the tensor product and equip it with a product where X tensor R times Y tensor S is the product of X and Y in L, tensored with the product of R and S in Z, minus the product of Y and X in L, tensored with the product of S and R in Z. In fact, there are other ways of turning a Zinbiel algebra into a different class of non-associative algebras. For example, it becomes a Lie algebra under the usual bracket product. If you define a new product X circle Y minus Y circle F, then Z becomes a Lie algebra. And if you use instead the Jordan product to take the product of X and Y to be XY plus YX, then it becomes a commutative associative algebra. And in fact, commutative associative algebras are the Koszul duals of Lie algebras. And in fact, there's a functor from Zinbiel algebras to commutative associative algebras, which is dual to the inclusion functor from Lie algebras, embedding them into Leibniz algebras. Okay, well, we define the usual series. Z to the power 1 is Z, and inductively Z to the power k plus 1 is Z times Z to the k. Multiplication on the left here, note, because we're dealing with a left Zinbiel algebra. And similarly, Z to the brackets 0 is Z, Z to the brackets k plus 1 inductively is Z to the brackets k multiplied by itself. And we'll say that an element of a Zinbiel algebra is left normed if it's of that form. In other words, it's just a sequence of products on the left-hand side. And then it's very easy to prove the following lemma by induction, very elementary induction argument, that every element of the Zinbiel algebra, that is the product of n elements, can be expressed as a linear combination of the same n elements, but with each term being left normed. And then we define Z to be nilpotent if the first of those series terminates in 0, and respectively it's solvable if the second, the derived series, terminates in 0. So the usual definitions. And of course, it follows from the lemma that in a nilpotent Zinbiel algebra, every product of n elements will be 0. Okay, well, notice first of all that Zinbiel algebras are right commutative. That is that xy times z is the same as x, z times y. So if you like, you can interchange the y and the z. And that's because using the Zinbiel identity, both sides of that equation are equal to x times yz plus zy. So they're right commutative, and the right centralizer of any element x in z is the set of elements of z which annihilate x on the right-hand side. Then there was an interesting paper by Zinbiel and Lemaire in 2005. And I apologize for my pronunciation of their names. I'm sure that was dreadful. And they proved a series of very interesting results. First of all, a very simple lemma, which nevertheless proves to be very useful. If you have a right commutative algebra, so not necessarily a Zinbiel algebra, then for every x and y and z, the right centralizer of x is sitting inside the right centralizer of x circle y. And that's very easy to prove from the identity. If you take an element z in the right centralizer of x and multiply x circle y on the right by it, then remember, right commutativity says you can interchange the y and the z, so you get xz circle y, and xz is 0 because z's in the right centralizer. So z is also in the right centralizer of x circle y. So couldn't be a much easier proof than that. If Z is a Zinbiel algebra and x is in Z, we define the left multiplication by x to be precisely that, multiplication on the left by x. And then a second lemma that they proved was this one. If Z is a Zinbiel algebra and x is in Z, then if V is an eigenvector of the linear transformation Lx, left multiplication, with eigenvalue mu, then in fact V squared is an eigenvector with eigenvalue a half mu. And again, that's not difficult to see. Because V is an eigenvector with eigenvalue mu, we have that x times V is mu times V. And then if you multiply both sides of that equation on the right by V, you get x circle V is mu V circle V. And then using the Zinbiel identity, xv times V, okay, the Zinbiel identity says that's x times V plus V times V. Okay, so it's twice x times V squared. And just rearranging those two equations, then you get that acting on V squared on the left by x gives you a half mu V squared. Okay, the third lemma then that they proved was this one. If you have a Zinbiel algebra of dimension n over an algebraically closed field f of characteristic different from 2, then for every x in Z, we have Lx to the n is 0. Remember, n is the dimension. Or there exists a non-zero eigenvector, y, with a non-zero eigenvalue, lambda, such that y squared is 0. Okay, well, again, not too difficult to see this. Of course, if Lx is nil, then Lx to the n is 0 by the Cayley-Hamilton theorem. So if it's not nil, well, again, by the Cayley-Hamilton theorem, it'll have a non-trivial eigenvalue, mu, say. So let Z be a corresponding eigenvector. Then by this lemma that we just proved, together with a simple induction proof, if Lx acts on V to the brackets k, then you just get 1/2 to the power k mu V to the k. Okay, that's just that previous lemma plus an induction. And then using straightforward linear algebra, then there exists an n which will be less than or equal to the dimension of z, such that v to the brackets n minus 1 will be non-zero, but v to the brackets n is equal to 0. So now just put y equal to v to the brackets n minus 1 and put lambda equal to a half to the power n minus 1 times mu. And that, of course, is non-zero because mu is non-zero. Okay, the next lemma then said that for every finite dimensional Zinbiel algebra over an algebraically closed field, there exists some non-zero x such that the right centralizer of x is the whole of z. Okay, this takes a little bit more proving, but so let me just sketch how the proof for this goes. First of all, we show that there's a non-zero element A0 such that the right centralizer of A0 is the same as the right centralizer of A0 times B for every non-zero B in Z. Okay, how do we do that? Well, first of all, pick any non-zero element of Z as your A0. It might work, it might not. If it works, all well and good. If it doesn't, then there must be some A2 in Z for which the right centralizer of A1 is different from the right centralizer of A1 times A2. But remember, the left-hand side there is inside the right-hand side. So by that lemma, the right centralizer of A1 will be strictly inside the right centralizer of A1 circle A2. Okay, well, now play this game again. Choose your A1 times A2 as your A0. And if we repeat that procedure, we obtain a strictly increasing sequence of right centralizers sitting inside Z. And because Z is finite dimensional, of course, that sequence must terminate. So let's suppose that it terminates with the last element that I've written down there. Then let's take that as our A0. And that has the property that we claim for it. Okay, now I'm going to take this to be x. So I need to show that the right centralizer of that x is the whole of z. Well, if Lx is 0, then of course that holds. That's saying precisely that right centralizer is the whole of Z. So let's assume that left multiplication by x is non-zero. Okay, let's deal with the characteristic 2 case first of all. Well, the Zinbiel identity gives that x times b, remember again, that's x times b times b plus b times b. So it's twice x times b squared. And because we're in characteristic 2, that's 0. So b must belong to the right centralizer of x times b. And from the way we've chosen x, that's the right centralizer of x. And that will be true for every non-zero b in Z. So Z is the right centralizer of x. Okay, what if the characteristic isn't 2? Well, we have this previous lemma that says that there are 2 possibilities that can occur. either Lx to the n is 0, where n's the dimension of z, or else there is this non-zero eigenvector with a non-zero eigenvalue whose square is 0. Now, in fact, that second case we can dismiss rather quickly. The latter is impossible because that says that B belongs to the right centralizer of x times B, and that's the right centralizer of x. And so that would tell us that lambda equals 0, and it's non-zero, so that's a contradiction. So we must have the first case holding. So there exists an m less than or equal to n such that Lx to the n minus 1 is non-zero, but Lx to the m is 0. Remember, Lx is non-zero, but Lx to the n is equal to 0. So there's some point in between where it changes over from being non-zero to 0. In other words, we can find an element C in Z such that if we act on C by Lx to the power n minus 1, the result is non-zero. And let's call that B. Okay, well then the centralizer of X, again by the choice of X, is the centralizer of X times B. And if you multiply B on the left by X, you're multiplying C on the left by Lx to the power m, which is 0. So that's the right centralizer of 0, and that's Z. So that proves lemma 4. Okay, well, using this then, they were able to show that Zinbiel algebras, in fact, are solvable. In order to do that, we need one more lemma, which says that every finite dimensional Zinbiel algebra over an algebraically closed field of dimension bigger than 1 has a proper non-zero ideal. Okay, well, by the lemma we've just proved, there is a non-zero element x such that the right centralizer of x is Z. Now we take Z times that x, the set of all elements, element little z in capital Z times x, call that J. Then first of all, we claim that that's an ideal of Z. So let's just see why that is. Okay, well, if we multiply a typical element of J on the right by A, then right commutativity says we can interchange the X and the A so that we get Z circle A circle X. And of course, Z times A is in Z, so that's in Z times X. In other words, it's an element of J. So it's a right ideal. What about multiplication on the left? Well, because the right centralizer of X is Z, if you multiply any element of Z on the left by X, we get 0. Okay, so let's take a typical element of J now and multiply it on the left by A. So you get A times ZX. Then just rearranging the Leibniz identity, that's equal to AZ times X minus A times X times Z. If you just take that negative term on the right-hand side over to the left-hand side, then you've got precisely the Zinbiel identity. So this is just a rearrangement of the Zinbiel identity. Now, the first term there is an element of J, because A times Z is in Z, so that's in ZX. The second term is 0, because the XZ in the brackets is 0, as we've pointed out in the line above. So, in fact, this is an ideal of Z. Okay, now we've claimed rather more. We've claimed that there's a proper non-zero ideal. Okay, so this is an ideal. Is it proper? Well, let's take a basis for Z, E1 up to En, with E1 equal to X. Okay, you can take X and expand it to a basis for Z. Then J, of course, will be spanned by the N products, E1 times X up to En times X. And E1 times X, well, E1 is X, so that's X times X, and that's 0. So, in fact, the dimension of J is less than the dimension of Z. So this is a proper ideal. Of course, it could be 0, but if it's equal to 0, then the one-dimensional ideal generated by X on its own is proper and it's non-zero. So in any case, there's always a proper non-zero ideal. Okay, then using that, then they were able to prove this theorem, that if F is an algebraically closed field of characteristic P greater than or equal to 0, so any characteristic, 0 or prime, then every finite dimensional Zinbiel algebra, Z over F, is solvable. And now, using that previous result, that's easy. We just use induction on the dimension of Z. Of course, every one-dimensional Zinbiel algebra just has trivial multiplication. So, of course, that's solvable. So starting off the induction is very easy. Just need the inductive step. So assume that n's bigger than 1 and the result holds for Zinbiel algebras of dimension less than n. Then by the lemma we've just shown, Z's got a proper non-zero ideal J. Of course, by the inductive hypothesis, J and Z factored by J are both solvable, and therefore Z's solvable. So over an algebraically closed field, any characteristic Zinbiel algebras are solvable. And that's the way in which they stated their result. But of course, you can get rid of the algebraic closure. The requirement of the algebraically closed field can be removed because if omega is an extension field of F, then Z tensored over F with omega is solvable if and only if Z is. That's true for any non-associative algebra. So in fact, finite dimensional Zinbiel algebras are always solvable. Now they went on to prove, using very detailed computations with elements, some further results. So let me just tell you what those results are. Say they're very detailed computations, so I won't go into the proofs of them. But first of all, if you have a field of, again, any characteristic, and Z, a solvable Zinbiel algebra with solvability length m, then if P is 0, or if it's bigger than 2m minus 1, then in fact Z is a nil algebra with nil index no greater than 2m. And conversely, if Z is a Zinbiel nil algebra with nil index m, and if P is 0 or P is bigger than m minus 1, then Z is solvable with solvability length m. So with some restrictions on the characteristic, then Zinbiel algebras are in fact nil algebras. Okay, in fact, that's always true for characteristic 0, but there are some constraints for characteristic P. The next result said that if, again, you have a field of any characteristic, then in fact, every Zinbiel nil algebra is nilpotent. So again, over a field of characteristic 0, Zinbiel algebras are nilpotent. And with some restrictions on the characteristic, in characteristic P, again, they are nilpotent. And in fact, more than that, if Z is a nil algebra with nil index m, then the nilpotency index of Z is no greater than 2 to the m minus 1. Simple corollary to that tells us that simple Zinbiel algebras aren't very interesting. Finite dimensional simple Zinbiel algebras over an algebraically closed field, again, any characteristic, is one-dimensional and has trivial multiplication. And one final corollary, every finite dimensional Zinbiel algebra over the field of complex numbers is nilpotent. And if P is bigger than 0, then every finite dimensional Zinbiel algebra over an algebraically closed field of dimension less than log to the base 2 of P plus 1, and characteristic P, again, is nilpotent. Okay, the arguments over the complex numbers used properties of complex numbers which certainly aren't shared by all fields. So I read this paper with much interest, and I thought, well, okay, so Zinbiel algebras are certainly solvable. There may be some cases where they're not necessarily nilpotent. So I thought, well, maybe then they're super solvable. And that's really what I set out to prove. But to my surprise, I turned out that rather more than that was true. In fact, they're always finite dimensional Zinbiel algebras are always nilpotent. And in fact, the proofs of that is rather easy. It's certainly much easier than the complicated calculations using individual elements. Of course, their results do give you more information than simply the nilpotency. And it really came out of this very simple lemma. If you have a right ideal of a Zinbiel algebra, Z, let's call it B, then if you multiply b on the left by z, you get a two-sided ideal of z. Okay, not very surprising, but in fact it's true. So if you multiply zb on the left by z, again using the Zinbiel identity rearranged, you can see that that's inside z squared times b plus z times bz. The first term there, of course, the z squared's inside z, so that's inside zb. And if you look at the second term, the b times z, of course, is in b because b is a right ideal. So that's inside z times b. We multiply it on the right by z, then this is essentially just using the right commutativity. If you like, the b and the last z can be interchanged to see that z times b all times z is inside z squared times b, and that's inside z times b. So zb is a two-sided ideal of z. Okay, well, that leads to the following result, that if you have a minimal ideal of a Zinbiel algebra, so a minimal two-sided ideal, and B is a minimal right ideal sitting inside A, then in fact A equals B. So a minimal ideal is also a minimal right ideal. So let me show you why that's true. Okay, well, Z times B is inside Z times A because B is inside A. And Z times A is inside A because A is a two-sided ideal. Z times B is an ideal, A is a minimal ideal. So that says that Z times B must be either 0 or A. Now the former tells us that B is an ideal of Z. Okay, that would say it's a left ideal and it's also a right ideal, so it would be a two-sided ideal, and so it's equal to A. So we just need to look at the second case. So let's suppose that Z times B is equal to A. Okay, well, look at B times Z squared. Not difficult to see, again, using the Zinbiel identity, that that's a right ideal. And because B is a right ideal, it will be inside B. So it's either 0 or it's B. I claim it can't be equal to B because if B is inside B times Z to the brackets K, then it's inside B times Z to the brackets K multiplied by Z to the brackets K. Just replacing the B by B times Z to the brackets K. And remember, by the Zinbiel identity, that will be inside B times Z to the brackets K times Z to the brackets K, which is Z to the brackets K plus 1. So if B is inside B circle Z squared, then it's inside B times every term in the derived series. But Zinbiel algebras are solvable. So that would say that B was 0, and it isn't so, because using the solvability, that implies that B circle Z squared is 0. Well, using that, we can see that B times Z is 0. Why? Well, B times Z is a right ideal that's inside B. So again, it's either 0 or it's equal to B. And now we can play the same game using solvability again, that if it's equal to B, then B is the same as B times Z times Z. And that's inside B times Z squared. And B times Z squared, we've just shown, is equal to 0. So in fact, B times Z is 0. Okay, well, now if we look at Z squared times B, so multiplication on the left by Z squared, it's very straightforward to check that that's also an ideal of Z. It's inside A, so again, it's got to be equal to A or to 0. The former, if it's equal to A, then in fact B must be inside Z squared circle B. And now we can use this solvability argument yet again. If it's inside Z squared circle B, it'll be inside every term in the derived series times B. And that can't be because of solvability. So therefore, Z squared times B is equal to 0. Okay, but now, well, if we look at A times Z, A times Z is ZB. Look up at the top of the screen, the top equation that's labeled equality. We're assuming that A is equal to Z times B. So A times Z is Z times B times Z. Zinbiel identity tells us that that's inside Z squared B. In fact, again, right, commutativity alone will do that. It essentially says you can, as long as you have an inclusion, you can interchange the B and the Z. So it's inside Z squared circle B, and we've shown that that's equal to 0. If we multiply on the A on the left by Z, then that's Z times ZB, again, using the equation at the top that A is equal to ZB. And that's inside Z squared B plus Z times BZ. Now Z squared B, we've proved is equal to 0. We've got that BZ is equal to 0, so that's equal to 0. So in fact, the dimension of A is 1, and B must be equal to A. So that proves our result. Okay, well, now it's not very surprising, looking at that proof, that if A is a minimal ideal of a Zinbiel algebra, then it's got dimension 1. And if you multiply it on the left or on the right by any element of Z, you get 0. So, say the proof is really in the proof of the previous result. A times Z is a right ideal. It's inside A. So because of what we've just proved, it's got to be A or 0. If it's equal to A, then, well, the A you can replace by A times Z. So you get A, it's equal to A times Z, which is inside A times Z squared. And we play the same game. It's therefore inside a times every term in the derived series of z. And solvability then tells us that a must be 0. So a times z must be 0. Similarly, if you look at z times a, that's also a right ideal inside a. And so it's either equal to a or 0. If it's equal to a, then it's equal to z times a, which is inside z squared a. And again, that same solvability argument shows that z times a is 0. And therefore, we have the result. Okay, well, it follows very easily from that, then, of course, that Zinbiel algebras over any field are nilpotent. Again, it's just a straightforward induction. It clearly holds if the dimension is 1. It holds for Zinbiel algebras of dimension less than k, and z has dimension k. If you take a minimal ideal of z, then L over A is nilpotent by the inductive hypothesis. So there's an n such that z to the n is inside A, and then z to the n plus 1, well, will be inside z times A, and that's equal to 0 by the corollary. So they're always nilpotent. Okay, well, for many classes of non-associative algebras, if you have a nilpotent algebra, then the idealizer of any subalgebra is strictly bigger than that subalgebra. Does that hold here? Well, first of all, we've got to decide how to define the idealizer. So I'm going to say that if A is a subalgebra of a Zinbiel algebra, Z, then the idealizer of A in Z, which I'll denote by I suffix Z of A, is the largest subalgebra of Z containing A, in which A is an ideal. Okay, it's not as straightforward to describe what that set looks like as it is for Leibniz algebras. However, it's perfectly okay as a definition. Some people, of course, would call that the normalizer of A and Z and denote it by N suffix Z of A. Doesn't matter which terminology you prefer. Okay, well, if A is a proper subalgebra of the Zinbiel algebra, then in fact there's a k greater than or equal to 1, such that z to the k is not in A, but z to the k plus 1 is in A. And then moreover, z to the k plus A is inside the idealizer. Okay, well, the first assertion is immediate from the nilpotency of Z. Furthermore, if you multiply zk plus A on the left by A, well, that's inside A times Z to the k, which is inside Z to the k plus 1, and A times A is in A, and both of those terms are, of course, in A. If you multiply it on the right by A, you get that that is inside Z to the k times A plus A. And then you need an induction proof, but it's a straightforward induction proof that shows that Z to the k times Z is inside Z to the k plus 1. Remember, Z to the k plus 1 is Z to the k multiplied by Z on the left, not on the right. Okay, but an easy induction proof shows this inclusion, and that's inside A. Okay, so the following results and then are immediate from that lemma. In a Zinbiel algebra, every proper subalgebra is properly contained in its idealizer, as for other classes of non-associative algebras. And maximal subalgebras, of course, are ideals. Okay, so that's really what I have the time to say today. The references are given there. My paper, I think, has now appeared online in the Journal of Algebra and its Applications, but not yet in paper form. So thank you for your kind attention.
Thank you, David. Very interesting talk. Are there any questions, comments, remarks? Nobody? I have a question, David. The Frattini ideal for Zinbiel algebras is just the derived subalgebra. Am I right?
Yeah, you're correct. Yes, it
Yeah.
is. Yes. Yes.
Okay.
And it follows quite easily
Yeah.
from the rest there. Yeah.
Maybe there is some question from the. Okay. There is a question from the chat. Some examples of Zinbiel algebras would be? The question is from Florin Nikita.
Sorry, the question, let me see if I can find the chat.
Yeah. He's just asking for some examples of Zinbiel algebras.
Okay, well, they're not and not difficult to construct. There are several in the paper by
Dive.
I'll go backwards. How do I go backwards?
He has several explicit examples and also extensions with
Yeah.
second homology, and then you get a lot of examples.
You do, yes. So if you look at the paper by the two, I don't know, are they Russians? Are they Ukrainians? I'm not sure where Zinbiel and
So Zinbiel is from Alma Ata, so
right.
he speaks Russian at least.
Yes, yes. But certainly there are several examples in their paper.
Okay, any other question? Okay, if not, let's thank the speaker again. Okay, so we will resume on next Monday at the usual time. Goodbye, everybody.
Thank you. Bye.
Bye, David.
Bye.